Hi everyone, this is Brian MacDonald, author of Practical Stress Analysis with Finite Elements, and today we're going to be looking at a 1D Truss tutorial using ANSYS Workbench. And we're going to look at a tutorial from the book itself. An example is done in the book itself, and we're going to recreate that using ANSYS Workbench. So just looking through the third edition of the book, and we're on example 1.3 starting on example 1.1 starting on page 16 of the book. So here we have a tapered rod. There's a load at one end and it's held in the other end. So if we go through the example in the book, you can see there's various description there of the elements and everything. But I want to get down to this point here where basically we're modeling the tapered rod as a series of 3 rods with uniform cross section. So we're going to have 3 rods or 3 elements with 4 nodes, so a node on each end of the element. This side here will be held rigidly and this side will have a force attached to it. So to go through the various calculations here, you can see on page 20 we form the stiffness matrix and then we solve the problem. In page 21 we get this answer here for the nodal displacement distribution, so we can see how much each point in the model has moved, and we're going to try and see how close to this result we can get. And then also on page 22 we have a stress result here, which tells us that the highest stress in the stepped rod is 59.72 megapascals. And again, we're going to see how close we can get to that again. So the important information for us at the moment is just to go back onto page 20. You can see we have the cross-sectional area of these 3 elements here. So 1, 2, and 3. And they have cross-sectional areas of 4.33 by 10 to the minus 4, 3 by 10 to the minus 4, and 1.675 by 10 to the minus 4. So it's going to recreate this model in Workbench. So I'm going to start off by opening up Workbench. So again, I'm using version 2019. And just going to open up Workbench. So when Workbench opens up, then the usual thing is, in this case, we want to do static structure analysis. So I'm going to click on static structural. I'm going to hold down the left mouse button and drag the static structural over into the project schematic. And then again, the first thing I want to do here is just save this and give it a name, just in case we have a problem, we lose anything. So I'm just going to go File, Save As. And so in this case, I'm going to save it to my temporary directory and I'm going to give it a name. So I'm just going to call this one 1D Truss. And go save, and we're ready to go. So the first thing that I'm going to look at then is the engineering data. If we go and take a quick look at the book again, we'll see that we were asked to use a linear elastic material model with Young's modulus for steel of 210 by 10 to the power 9 pascals, or 210 gigapascals. So if we go back to Workbench again, you can see there already is a structural steel there, which is similar enough to that. But what I'm going to do here is add my own material. Okay, so I click on the box here and I'm going to call it my steel. Okay. And my steel at the moment has no properties, so what I'm going to go over here is I'm going to click on linear elastic, and I'm going to double click on isotropic elasticity, and you'll see that's populated over here under my steel. In there then I'm just going to give it 210 e to the 9 pascals, and I'm just going to give it a value of 0.3 for Poisson's ratio. So that's my material, my steel material defined. So I can close the engineering data now. And the next thing I want to do is open up the design modeler. So I will right click on geometry and click on new design modeler geometry. And the design modeler will then open up. So here's the design modeler. So again, I want to draw on the XY plane. So I'm going to click on the XY plane. I'm going to click on look at plane. I'm just going to go back to the book for 1 second and just look at some of the dimensions of the model. So the model is 0.6 meters long, and it's divided into 3 evenly shaped elements. So there's going to be like 0.2 length of each of these elements. So if I go back to the design modeler again, what I'm going to do here is I'm going to click on the sketching tab, and I go down to settings, And first of all, I'm going to check my units up here. So in units, I notice I'm using meter and degree. So that's what I want. I want to use the SI unit system. In grid here, I'm going to say show the grid in 2D and turn on the snap. Change the major grid spacing to 0.2 of a meter. So you can see now the grid has disappeared because I'm far too zoomed out to see it. So what I'm just going to do is zoom in there. So I'm holding the control key and just moving in. Or you can use some of the buttons up here to zoom in. So I just want to get in where I can see about 3 of those on the screen. Okay, so maybe about there. So now I'm going to click on draw up here. And what I want to do now is to create 4 construction points. Okay, so I'm going to click on construction point. I'm going to put the first one at the origin. Second one out here, so you notice it'll snap to that. Second one here. Third one, sorry, and the fourth one there. So now I've got 4 points. Okay, now what I want to do is dimension in between those points. So I'm going to click on dimensions here and horizontal. And up here, I notice I have 2 selection filters on, points and edges. Let's turn off the edges for the moment and just have points. So I'm going to click on that point and this point and drag my dimension up there. And you can see it's already 0.2 meters. And just do the same thing again for the other ones. So again, just make sure we have all of these at 0.2 meters. Okay, so I've got 4 points and they're all 0.2 meters apart. Okay, so now what I want to do is I want to create lines in between those points. So I'm going to go up to Concept, Lines from Points. Okay, so I'm going to click on the first point here, and I'm going to hold down the Control key and click on the next point, and I'm going to go Apply. So that's created one line, and then I generate to create that. I'm going to do the same thing again, Lines from Points. I'm going to click on the first one. I'm going to hold down the Control key, click on the second one, and this time, after I hit Apply, I'm also going to change from Add Material to Add Frozen. The reason for that is, if I click on Add Material here, it will just extend this line to make those 2 lines the same, and when I try and go and apply different cross sections later on, it won't work. Okay, I want different cross-sectional areas in these 3 lines, so I have to change that to Add Frozen. So I go Generate, and then I do exactly the same for the last one. Concept, Lines from Points, click on the first one, hold down the Control key, click on the second one, go Apply, change that to Add Frozen, and then hit Generate. So now if I click here, I've got 3 line bodies. Okay, so I have 3 different lines there. And you'll notice that there's a problem here in yellow, that there's no cross section selected. So now what I want to do is define cross sections. What I want to do here, just jumping back to the book for a minute, is on page 20, it tells us the cross-sectional areas of each element. So element number 1 is 4.33, element number 2 is 3, and element number 3 is 1.675, all by 10 to the minus 4 meters squared. So I want a cross-section that's going to have that area. The simplest way to do that is to define a circular cross-section. So let's define the first one. So concept, cross-section, and I'm going to go with circular here. Okay, and I want to get that area there to be, again, let's just go back here, to be 4.33 by 10 to the minus 4. Okay, so jumping back to the design modeler again. So by a little bit of simple mathematics and using, the area is equal to pi r squared, I can do a few calcs and work out that the radius of 0.01174 here gives me the cross-sectional area that I want, which is 0.000433 meters squared. Okay, so that's my first cross-section. I need to create 2 more of those. So again, create a second cross-section, circular, again. And this time I need to put in the value that's going to give me the desired cross-section. So in this case, it works out to be 0.009722. Okay, and that's giving me 29693. So I'll maybe just tweak that a little bit so I get the exact value of 0.003 in here. Okay, so if I put in 0.009772, I get 0.003 meters cubed, which is what I want. And then creating the third cross section. And again, in this case, I want to get to 0.0001675, and here I'm putting in 0.007302. So that's the radius that will give me the desired cross-sectional area. So now if I go down to the line bodies again, and I click on line body 1, so this is the one that has to have the first cross-section. So I click on the yellow here and change it to circular 1. And the second one, I want to have the second cross-section. I change that to circular 2. And the last one, I want to have the third cross-section, so I change that to circular 3. Now what I can just do to check this is I can go up here to View, and I can change the view to cross-section solids. Okay, so now you can see it's looking like I expect. I've got a thicker cross-section here, slightly thinner one there, and a thinner one again there. So that looks quite good. Again, if I want to get out of the plane view and take a look at the isometric view of that, you can see I've got 3 rods, and they're of varying cross-section. Now the problem with this model would be if I went and tried to solve this now, even though I have the 3 rods, they're not seen as being connected to each other. So if I put a load on here, they would essentially just pull apart. So what I now have to do is tell Workbench that these are all one structure. So what I'm going to do here is click on 3 parts, 3 bodies, right click on it, and so sorry, not actually right click, but click on 3 bodies, and hold down the control key and select all 3 bodies, and then right click on one of them, and you'll see this form new part turn up here. So I click on form new part. Now I have one part, but that one part is made up of the 3 bodies. So now these are seen as being one structure. Okay, so I can now save my project, and I can close down the design modeler, and I'll open up the Workbench schematic again, so you can now see geometry is a tick beside it. The model needs some work, so let's double click on model to open up the mechanical modeling. Okay, so mechanical has opened up. You can see right here I have a line on the screen. Again, we may want to go to display and change that to cross section. So now you can see the cross section if you want. You can turn it off again if you prefer. Okay, I'm just going to leave it on for the time being. Let's just work our way down through here. So geometry has one part which consists of 3 line bodies. They all have structural steel assigned to them. So what I'm just going to do is just change that now to my steel. Okay, so again, remember we set up our own material. This won't make a lot of difference, to be honest, in this analysis, but again, just so to learn how to change materials. So again, if I click on any of them, you should see my steel turning up there. Again, we can look at the cross sections if we want to get information about them, so on. Then the next thing we notice is that there's a lightning sign beside the mesh, so we need to make a mesh. So the first thing with meshing truss elements is what we don't want. Normally we divide the region into lots of elements. Truss elements don't work like that. They just need to have one element for each line. So we need to make sure that's what the mesher does. So I'm going to right click here, and I'm going to insert sizing. Okay. And I'm going to make sure that the geometry selection up here it's set on face. I'm going to change it to edge. Okay, so I don't want to just pick those lines. So I'm going to pick the first line. I'm going to hold down the control key. I'm going to pick the second line and the third line because I want all of them to have one division. And then in here, I'll go apply. And it says then the type of definition I want. So it's not element size, it's actually number of divisions. And I want them all to have one division. Okay, so that's what I want there. That's fine. So now I can go up to mesh, and I can right click, and I can go generate mesh. So now it'll generate the mesh, and you can see it's just generated one element in each case. Okay, so there's one element, there's another one, and there's another one. Okay, so now I'm almost ready to solve. I just have to put some loads and boundary conditions. So I go into static structural. I right click again. I'm going to go insert, in this case fixed support. And again, I want to make sure that the selection here is on a vertex, not on an edge, because I want to pick the point at the end there. I want to pick that point right there. And I'm going to say apply a fixed support to there. So that point can't move. Now similarly, I'm going to right click again and go insert. And in this case, I'm going to pick force. And the first thing it says, well, where do you want to put it? Again, I want a vertex selected, and I'm going to pick the end here. I'm going to go apply. And then it's going to ask me to define the force. I'm going to first of all say by components, and I want it in the x direction. And if we go back to the problem and take a look at that, it asks us for 10,000 newtons in the x direction. Okay, so you can see I've got an arrow on there. Okay, I'm just going to maybe zoom out a little bit here. And if I kick back on static structural, you can see I have a fixed support there, and I have a force of 10,000 newtons there. Okay, so the next thing then is I'm going to tell it, well, what kind of results do I want? So again, I'm going to right click here, I'm going to insert. In this case, we're going to look at a beam results and the beam tool. So we're going to insert a beam tool, and the beam tool is there. It's already got direct stress and combined stresses in there. Let's also put in deformation, and we're interested in the x deformation. Okay, so I'm going to go directional, and in directional there it says x-axis. That's what we want. Okay, so now I am ready to solve this. So good idea to always just save it before you solve it, just in case something happens. So I click on solution, and I can either click on context up here and go into the solution menu and click solve, or I can right click and click solve. Just going to go ahead and do that. We'll just wait for the solver to solve it. Shouldn't take too long, so it's a very simple problem. Okay, so now the solver is finished, and we can see green ticks beside everything here, which means we've gotten some results. So the first thing we'll do is take a look at the directional deformation. Okay, so it's telling us that the maximum deformation is 0.00011,068, and it's at the end of the bar. Okay, so let's just quickly jump back to the book and just see what results we got on page 21. You can see that the displacement at the end of the bar is 11.062 by 10 to the minus 5, which corresponds quite well. So 11.068 versus 11.062. That's close enough. Again, we can probe those results if we want to find out at specific points. So this is giving us kind of a what this is doing is it's working out the displacement at each of the nodes, at each of the points, and it's interpolating in between them. It's making a simple linear interpolation in between them. Let's just get a probe and just see what the exact displacement in the x direction is. So here you can see it's 2.25, 2.3, and here it's 5.4, 5.5. Let's go and have a look at our displacement results. Okay, 5.3, 2.1. Okay, so we could probably get the exact points there and find we'd have more or less exactly the same thing. Okay, so we're not too far off. Let's take a look at stress then. So direct stress, this is a bit easier to read. So we've got the red value, which is 59 megapascals, so 5.9 by e to the 7 is 59 megapascals. Have a go and look at the book on page 22, and here's our stress at the bottom here, 59.7 megapascals, 33 and 23 at the three nodes. So it's the three elements. So we've got 59 there. The blue one is 23, and this one in the middle should be 33. So again, we just can probe that. Yeah, perfect. 33.36 megapascals, 59.745. 23.11. Again, very, very close. Okay, slightly off maybe in that one, but very, very close. Okay, so that's a very simple tutorial using ANSYS Workbench to verify one of the examples in the book. Just shows you how you can check your answer if you're trying out some of the questions. So if we go back to the book, if you look at the end of chapter 1, there is one or two questions there. Okay, so it's given us another question, a number question. So you can maybe try that one out and check your answer using Workbench to see if you get a similar enough answer. So that is the end of this presentation. So again, just reminding you that This 1D Truss tutorial is from the book. It's an example used in the book. There's a lot more information in the book. There's a lot of help in the book with doing finite element analysis. So I strongly recommend you get a copy of the book. And as always, I'll put a link to the book in the description. So thanks very much for watching, and see you next time.